Hello, fifth year. This is our first video lesson, so hopefully you can all hear me clearly, and you can see this video on Firefly without any problems. So we'll give it a try, and I'll be on Teams if there's any issues. So we've looked at revision last week, and how the fourth year material ties into fifth year. Now this booklet we have on the screen. Uncertainties is the first topic of the hire. So usually in class you would get this booklet given out to you. It takes about one period, maybe a period and a half to go through. It's basically looking at how to make our values more accurate and how to just be generally more accurate and precise in all of our work. Now you may have heard the analogy of the dartboard when it comes to accuracy and precision, which is shown on the front of the booklet here. And if you ask people on the street what is accuracy and what is precision, often they will struggle to tell you the difference between them. Now, low accuracy, high accuracy, and low precision, high accuracy and high precision are three things to consider. If you look at this first dartboard, what you'll notice is that all of the arrows have hit the target roughly in the same area, and spread is not that great. Now they're not near the middle, okay? They're not on the bullseye. So you're aiming for the bullseye. You've not been very accurate. However, you have hit the same area 3 times, so you have been quite precise. If we look at the second dartboard, high accuracy but low precision, we have close to the bullseye, okay? They're in the red zone. They are not all in the same area though, they're not grouped nicely, so you're not being very precise. If we look at our third example, high accuracy and high precision, you can see that they have hit the centre, our yellow bullseye, and they are all grouped nicely together. So, what do we mean by accuracy and precision? It's hitting the target where you want to and hitting it consistently. And ironically enough, I'm just going to have to close the window as my neighbours decide to cut their grass. So hopefully that is a bit clearer now that I've closed the windows. So first thing to think about accuracy and precision and the difference between them. There will be a video on Firefly which will go through what I've just said again for you to watch. And it talks about shooting an apple which is on top of somebody's head with an arrow. So all of the booklets follow the same style as National 5. The first page tells you really what you're going to learn in this booklet. We're going to talk about using appropriate units and prefixes. We're going to talk about significant figures. And we're going to talk about scientific notation. Then we're going to talk about uncertainties. This is just being aware that any reading you take in an experiment is subject to some sort of uncertainty in the value. So this booklet, obviously, I don't want to go on for an hour in a video, so I'm going to highlight the key areas, talk to you about the important theory, and then give you a chance to read through it at your own pace and try some questions. So symbols and units are obviously important in physics. You always have to include the correct unit and symbol in your answer or you will lose a mark. This just gives you a sort of index of symbols and units that we use. Some of them you'll be familiar with, for example, are displacement, distance, both measured in meters, speed and velocity, meters per second, weight is the Newton. So you can see below there are some new units here that you may not have seen before. For example, impulse. These are just the higher units that you'll end up covering throughout the year. So I wouldn't spend too much time studying this table. That's just going to be an index of units. If you're looking for an answer, and you're looking for a unit to put in an answer and you can't remember which one it is, you could use this page here. A few more. Again, I would just going to graze over these just now because you've not studied the course, so a lot of them don't mean anything to you. This bit I would say is important, prefixes. So pico, nano, micro, milli, kilo, mega, giga, and tera. You hopefully have heard of all of those. If you've not, don't worry. Pico being the smallest and tera being the largest. You usually will not see anything outside of nano and giga. So we just have included pico and tera in there in case the SQA decide to throw in a little surprise in the exam. However, prefixes are very straightforward if you are aware of the scientific notation in your calculator. Always in physics, the final answer can have no more than, there we go, I can have no more significant values than the value with the least number of significant figures used in the calculation. So what does that mean? If you're going to give an answer, trying to give it to two significant figures and no more. Okay, that would be the rule. I would say no more than two significant figures. That should keep you safe. You could use three, again that would be safe, but no more than two or three would be ideal. The physics formulas that you'll end up knowing at the end of the year are detailed in the formula sheet. Again, not going to spend too much time on this. Additional relationships, again, this is given to you in the exam. Trigonometry, circles and spheres. These will be used to help you work out some answers as you go through the material. So uncertainties. All forms of measurement are liable to an uncertainty. This can be expressed in a percentage form. The two types that we are interested in are usually systematic and scale reading. Systematic is when you take readings that are too large or too small, and scale reading is how well you read the instrument. For example, if I was to ask somebody how tall they are, usually they would answer you in meters or feet. Now, if I gave you a ruler that only had a meter marked on it and no centimeters and asked you to take your height, you may only be able to tell me that you're somewhere between 1 meter and 2 meters. And this is not very accurate. There's a large uncertainty in that height. If the ruler had centimeters marked on it, you may be able to tell me you're 150 centimeters exactly. If it had millimeters, you may be able to tell me you're 150.5 centimeters exactly. So systematic errors occur when you are taking readings that are too large or too small, and these are usually down to experimental design and the equipment you are using. Scale reading uncertainty is how well can an instrument be read. Now, a digital ammeter or voltmeter, you can read that quite easily. It gives you a value on the screen. For example, if you were looking at the depth of water in a beaker, that may not be as easy as the water tends to rise up around the edges of the beaker. So you would struggle to measure very precisely the depth of the water because you would be measuring the edge and not the centre. These things can cause some uncertainty. Two very easy examples. Now, if you look at an alarm clock, the uncertainties arise from mistakes in the way it is set up. A clock could run slowly or not zeroed. Again, another example would be measuring your mass. If you stood on the scales and they already had 10 kilograms on them before you stood on them, you're going to have an answer plus or minus 10 kilograms because you didn't zero it. An example of scale reading uncertainty here, you can look at this pencil. Now, if I asked you to tell me which length is the correct length for the pencil, I'm able to zoom in due to using the laptop. But on a bit of paper, it may be very tricky to precisely see where this pencil, that is the wrong pen, that's the pen I've been using with the first years. Let's go for a suitable pen for hire. Okay, you can see there that we know it's roughly 36 centimeters, 36 I would say. Now, if you were to view this on the page, that may not be as easy to point out. So 36 millimeters, sorry, not centimeters, is probably the best estimate. Now, the range of value for that is 35.5 to 36.5. Here, if we're looking at this voltmeter, there is no markings on the scale between 5 and 6. Therefore, we are not able to tell exactly what the value is. The probable best estimate is 5.3, and it could be between 5.2 and 5.4. This is the important part. that when we are using a digital device, we always use plus or minus 1 of the smallest interval on the display as the uncertainty. So if the stopwatch shows 4.37 seconds, all we know is the reading is more than 4.36 or less than 4.38. This would be written as plus or minus 1 millisecond. Random uncertainties, these are uncertainties that cannot be completely removed from an experiment. Anything you carry out in the classroom will be susceptible to temperature changes in the classroom. This can change the pressure. Your supply voltage coming through the mains may change. These are things out with your control for you to identify when you write up your evaluation of an experiment. Let's have a look through experiment 1. So we have a trolley rolling down a ramp, and we're measuring the distance with a ruler and the time with a stop clock. The person looking at the ruler may not exactly get the distance correctly. This depends on how they are viewing the ruler. Okay, if they're looking directly down, they will see the correct length. If they're looking at a different angle, they will not see the correct length. Looking at an experiment, figure out where things could go wrong. That usually highlights systematic uncertainties. Random uncertainties, we use a stop clock. The user's reaction time is likely to be the most significant. Just highlight this all. Source of error. If you used an electronic timer, this would take away human error. Okay, so in this case, to get used to writing on the laptop again, human error. You could repeat your experiment several times to find the average value. Any measurements which differ greatly from others may be ignored as a mistake. So if you look at these readings here, 9.66, 9.26, 9.58, 8.42, 9.32, 9.36. It's clearly obvious that this was a reading that we didn't do correctly. So you would work out your average from the other values. This reading was omitted as it obviously disagrees. The stop clock may well have been misread at that time. So to find out the random uncertainty in our values, what we want to do every time, and we use this formula, is maximum reading subtract minimum reading divided by the number of readings. Okay, so that helps us find the random uncertainty in our answers. So here, the maximum 9.66, take away the minimum 9.26, divided by 5, that's how many readings we used, tells us that the random uncertainty is 0.08 seconds. The reading uncertainty and the random uncertainty together show 0.01 seconds and 0.08 seconds. Now, good practice is to, in your final answer, only give the uncertainty which is likely to have the most effect. It's clear here the random uncertainty 0.08 seconds will have the largest effect. So the time it takes for the trolley to roll down the slope is given as the average time plus or minus the biggest uncertainty, 0.08 seconds. There are some other experiments here that I'm going to let you read through on your own because it's just sort of repetitive of how to apply these rules. This booklet will be pasted into Firefly, and obviously you can watch this video as many times as you need. I would focus on the table and how to use the values. So in this example, our distance, we've got 5 readings. We have the average of the distances. To find the random uncertainty, we take the maximum, subtract the minimum, and divide it by the number of readings. That gives us 0.0012 meters. If you have a look, we can see we've displayed the reading uncertainty. That was taken from the fact they looked at the ruler. the random uncertainty taken from our formula, and we have chosen to go with the 1.041 plus or minus 0.001 meters. Okay, we have rounded this value here. Now, the best estimate of value of the average speed is calculated using the mean distance and the mean time. So we take our average speed equals distance over time, 1.041 divided by 9.44 gives us 0.11 meters per second. Go to skip forward to the summary page. This is probably the most important section. It gives you an index of how each uncertainty is calculated and how it is displayed. So you can make sure that you've read through systematic, scale, and random. Look at the examples to see how, if you were completing a question, you would write down the values. Here's our formula to work out average, which I'm sure you know. Here's our formula to work out random uncertainty. We have some worked examples for you. Take your time to go through these, try them yourself. They will be really useful. Example 3 is where we calculate the average uncertainty in a percentage. So if two or more different quantities are measured and combined in some way, when the measurement with the largest percentage is the most significant, and determine the final percentage of uncertainty. This can appear complicated, but what we're interested in here is a simple experiment. We have voltage and current, and we know that R equals V over I. So first of all, work out the uncertainty in the voltage, work out the uncertainty in the current, and work out what that uncertainty is as a percentage. Okay, 0.2 divided by 6.2 tells us times 100 is a 3.2% uncertainty. 0.1 divided by 1.5 times 100 gives us a 6.7% uncertainty. The largest uncertainty is clearly in the current. So when we use the formula R equals V over I, we apply the uncertainty to our final answer. So 6.7 is our final answer for our uncertainty. 6.7% of the resistance is 0.27 ohms. So 4.1 plus or minus, now this is the tricky bit in the notes where they skip a section, 0.3 ohms is our final answer. R equals V over I, 6.2 divided by 1.5 equals 4.1. 4.1 plus or minus the largest uncertainty is 0.3 ohms. Again, take your time to go through this in your jotter and have a go at using the formula and the numbers yourself. Here there are a list of questions. This will be today's classwork and homework for next time. The answers are provided at the side, so you can check you're getting them right. I will post the answers to any questions that you have on Microsoft Teams and Firefly, and I will share the answers to these sort of past paper questions as well. If you've got any problems, then please message me via Teams or an email. Thank you.